Well, I hope that everybody had a good weekend. Let me kind of give you an idea of what's going to be happening this week and the next couple of weeks. Today, we're going to go ahead and wrap up this lesson we got over the vector word problems. Now, there's going to be a few that we're not going to be able to get to in class, and I would encourage you to go ahead and take a look at those. The answers are posted online along with the notes. So if you do have any questions about them, you can come on in and let me help you with that. The quiz that we took on Friday, I am going to go ahead and give you another little worksheet at the end today just for practice. Okay. Hello. How you doing? It's not going to be for a grade, but I'll talk about it just a little bit because in 1 week on Monday the 2nd, that's when we're going to have our first exam. So we are going to go ahead and start the next lesson tomorrow over vector dot products. I'm going to show you about vector projections, but that material will not be on the exam. It's only going to be material from the vector word problems and last week's lesson. Basically, a summation of the homework you turned in on Friday. Okay, so you definitely want to go ahead and start taking a look at that. Later in this week, on Thursday the 27th, we're going to have a CFA quiz over the same material from last week because we're not going to be able to complete the material we begin tomorrow. But what does that mean, CFA quiz? Do I have what, sir? A clipboard. Oh, see, or you can probably use one of these books down here if you like. Okay, there you go. So remember the CFA quiz is what? There you go. So you'll be plugging your answers in online via the Chromebook, but again, I'm already predicting that I'm going to be grading them by hand, just in case some of those open-ended questions don't record your answer correctly. So that's coming up this week. In fact, this week is pretty much just going to be a normal week. There's no happy minutes. Tutorials are back to normal. There's no drills this week that we have to worry about. In fact, it's really the last full week of instruction we have before spring break, because next week we have the test on Monday. Then on Wednesday of next week we have the what? The SAT, so I will not be seeing you guys that day. I'm going to be administering the exam myself. Then Thursday and Friday of next week, we're going to take our post-test. Do you guys remember at the very beginning of the school year, I gave you a test over all the material that we'll see throughout the year? Okay, we're going to go ahead and do that again, now having gone through the majority of that material. So basically, I won't see you one day next week, and the 3 days that I will be tests. And then the last week before spring break, Monday and Tuesday of that week, we have the 9 weeks assessment. So there's no instruction going on there. And then the last Friday, the 13th before spring break, I'm going to be out of the classroom grading internal assessments. So the last 2 weeks before spring break, there's really only 3 instructional days that we're going to have. So a lot of time is going to be lost for all those assessments, but it's one of those things we have to do. I think that's all I got, unless anybody has any questions. Okay, well, let's go ahead and wrap this up. We didn't have the opportunity to look at this on Friday because we came in, we did our happy minutes, we talked about the homework, and then we went straight into the quiz. And if you haven't noticed, the class average for you guys was 53.1. Okay, so it was the lowest out of all the classes, but we are going to talk about it tomorrow. I'm not passing the tests or quizzes back just yet because in both first and second period, there were a larger than usual number of people who were gone for different activities. So now that I'll get those taken care of, I'll pass them back and we'll talk about them tomorrow. But if you want to retake, remember you have until Friday morning by 8:05. Okay, so let's do a quick recap since it's been since Thursday since we talked about this. We started the lesson talking about bearing. Now, quadrant bearing is always given in this notation. So it starts out north-south and finishes east or west. So quadrant bearing is restricted to a quadrant. The measurement has to be an acute angle. Okay, so it's not going to go above 90. And the angle is always created between the y-axis and the vector that you're drawing. Now that's different from a true bearing, which always rotates clockwise from true north. So this is always written as 3 digits, and there's no north, south, or east, west written here. Okay, so then we went through several examples. I started to show you a process for these problems. In fact, I went ahead and worked them both ways. The idea is that the 2 vectors that were given, let's call them vectors 1 and 2. If I take the sum of those 2 vectors, it gives me what specific vector? What's that one key word? It starts with an R. The resultant. There we go. Okay, by adding the two vectors that were provided, it gives me the resultant vector, which we can then use to answer the question. So we did, several examples of those. Here we got the golf game. I want to go ahead and start with this one. Okay, now this one's a little different than the others. It says a runner's resultant velocity is 8 miles per hour due west, running with a wind of 3 miles per hour north 28 degrees west. So it's giving me a measurement in quadrant bearing. What is the runner's speed to the nearest mile per hour without the effect of the wind? So we're going to be using this formula in this problem. We multiply the magnitude of the vector times cosine theta, the magnitude of the vector times sine of theta. Okay. The only thing about this formula, remember, theta is always measured to start from where? The positive x-axis. So whether we're going clockwise or counterclockwise, we always start from the positive x-axis for this angle theta. All right, now let's think about this. We've got two vectors, and we want to end up with a resultant. Well, the reason this problem is different is because you're provided the resultant. So we want to go ahead and work backwards and figure out exactly what one of the original vectors is. So let's say v sub 1 plus v sub 2 is equal to the resultant. So we have the resultant. Okay. The other vector that I'm provided is the wind, which is 3 miles per hour at this quadrant bearing. So we have that. So the only thing we don't have is the vector which represents the runner. Okay, the magnitude of which would be the runner's speed that we're trying to find. Okay, so why don't we go ahead and set up our equation here? We have no idea what the runner's vector is, so I'm just going to go ahead and start off with AB plus, now in order to write the wind vector, we're going to need to use that formula. What's the magnitude of the wind, or how fast is it blowing? 3 miles per hour, okay, times cosine of what? Yep. Hey, and guess it's also on the website too. Okay, Thursday.
Where's Thursday?
The one that says Thursday. Okay. All right, there we go. Anybody else need that paper? That's okay. Okay. So what am I going to put in for my angle theta here? Remember, my measurements given to me is north 28 degrees west. Okay, so now Noe says 28, but we're not quite right. Let's think about this. What quadrant would north 28 degrees west put me in? That's in the second one, because here's north, here's west. Now remember, quadrant bearing, the angle is always created between your vector and the y-axis. So I would be looking at something like this. Let's say this is the wind vector. Its magnitude is 3 miles per hour. So the 28 degrees would be this little angle right here. But remember, what did I just say about the formula with respect to theta? It's always measured from what? It's always measured from the positive x-axis. So how can I easily find that value, Connor? There you go. So what is 90 plus 28? 118. So I actually want to go ahead and plug in 118 degrees. That's the one thing you really need to be very careful about. You want to make sure that you're putting in the correct angle measurement. Sometimes it's what's given in the problem. Sometimes it's not. You have to be able to tell the difference. So what's the rest of this vector? 3, the magnitude times sine of 118 degrees equals. Now, we do have the resultant given to me. This is one of those cases where we don't necessarily have to use the formula. We can if we want to, but if it's in a direction that's on an axis, we could just go ahead and write it out. So let's see, it's going 8 miles per hour due west. So can anybody tell me what that component form should be? Negative 80. Remember, the component form acts just like an ordered pair. So if I want to go left of the origin, well, it'd have to be negative. Would anybody like me to go ahead and apply the formula to show you that you're going to get the same thing? Any takers? We're all good? Okay, if you change your mind, let me know. All right, so we have the runner's original vector Okay, we're going to add that to the wind vector that we're about to approximate in just a minute. And it equals my baby, the resultant. Is my baby okay? Who dropped my baby? Adrian? Couldn't have been you. Couldn't have been the guy who raised his hand. All right. Okay. So let's go ahead and approximate the component form for the wind. So first I need 3 cosine of 118. All right, so I'm going to come on over here to my calculator. Let me get rid of all these calculations. So 3 cosine of 118. So I'm getting negative 1.41, let's say. Okay. So I have AB plus negative 1.41, comma. Now I want to approximate 3 sine of 118. Let's see here. 3 sine 118. What would that give me? Okay. So let's say 2.65. If we go ahead and round it to the nearest hundreds. So 2.65 is equal to negative 80. Okay. And can everybody see how we've set up an equation where I can easily find the component form for the original runner? Okay. Now, this is something that I like to do when I add or subtract vectors. I mean, when you do it as well, you're going to add or subtract the x's, add or subtract the y's. So I would go ahead and create an equation. I would say a minus 1.41 is equal to negative 8. And then solve for a that way. But I am noticing that a lot of my students are just using the component forms themselves. Like they're taking this whole vector and they're just subtracting it over. Would you guys like me to do that or stick with the original? Just subtract it over? Okay, let's do that. So I'm going to go ahead and say that a comma b is equal to the resultant, negative 80, minus, because we're subtracting it, it's plus over here, the negative 1.41, 2.65 component form for the wind. Okay, and now we can easily figure out what A and B will equal. So I need negative 8 minus that negative 1.41. Now, even though I went ahead and rounded on my paper, I'm going to go ahead and use the exact values in the calculator. So I need to go ahead and subtract this right here. So it looks like for A, I'm getting negative 6.59. Negative 6.59. And then I need 0 minus 2.65. Well, that's easy. Negative 2.65. This is the vector that represents the runner's original direction and speed. Okay. Now, the magnitude of the vectors that I'm given, they're all in miles per hour. So my magnitude is speed. So how can I find the speed or the magnitude of this runner's vector? What was that formula? There you go. The square root of a squared plus b squared. All right. So I'm going to go ahead and find the magnitude of this vector. So the square root of negative 6.59 squared plus negative 2.65 squared. And let's see what we got here. I'm going to go ahead and say square root. So we have parentheses. I'm going to go ahead and highlight this one just like I did before. Squared plus parentheses. Now I need the negative 1.41. Is that right? Negative 2.65. My bad. Okay. So I need that one. So I need to highlight this one. And then close parentheses squared. Okay. So this is going to find the magnitude of the runner's vector, but that will be the speed that the runner was traveling before the wind affected him or her. I don't know what gender the guy or girl or whatever it is. But what should I get when I push enter? What's that, Connor? There you go. Okay. So 7.2, I got 7.1. I'd say that's perfect. Okay. So about 7.1 miles per hour. Okay. There we go. Now the resultant speed the runner was traveling 8 miles per hour. So was the wind actually helping or hindering the person? Actually helping the person. So I guess we have to believe that it was blowing from the individual's back. Okay, now remember, we're in a two-dimensional setting, so 3 dimensions kind of changes things, but we'll see that when and if we are able to get there. Any questions on this problem? Okay. Now, the problem doesn't ask for it, and we won't find it, but let's say it did also want me to go ahead and find the direction angle theta for that vector we found. What formula would I be using? It's one of our 6 trig functions. The tangent one, there you go. It'd be tangent of theta equals, what ratio would I use? B divided by A. Now remember, just like the component form formula, that's going to start theta from the positive x-axis. Okay. All right, good. Well, let's take a look at another concept here. 2 or more vectors with a sum that is a vector R, that's what we're calling the resultant, are called components of R. So all those word problems that we were looking at prior to this, the 2 vectors that we added together, those can be referred to as components of the resultant that we were finding. All right, now while components can have any direction, it's often very useful to express or resolve a vector into 2 perpendicular components. We refer to these as the rectangular components of a vector. Basically, that means the 2 vectors that you would add to get the resultant form a right triangle. You've got one horizontal and one vertical. Those are called the rectangular components. Like in this diagram right here, the force R exerted to pull the wagon can be thought of as the sum of the horizontal component force X that moves the wagon forward and a vertical component force Y that pulls the wagon upward. So imagine you're pulling this wagon behind us. You're lifting the handle behind you and up. So think about the direction of that force. Well, if I break it down into these rectangular components, you're pulling it both horizontally and vertically up. Does that make sense? Okay. So that's what we want to go ahead and do here. So let's try a problem. It says a player kicks a soccer ball so that it leaves the ground with a velocity of 44 feet per second at an angle of 33 degrees with the ground. A, draw a diagram that shows the resolution of this force into its rectangular components. Okay, so basically we have it here. We just haven't drawn the rectangular components. Let's say that this red line here is the ground. Okay, so remember we're in a 2-dimensional setting, so the ball is kicked up and to the right. Okay, and we know a couple things about this ball. This vector represents the ball itself. So how fast is it traveling? 44 feet per second, so that is the magnitude, that's the speed. And what angle does it create with the ground? 33 degrees. Okay, so 33 degrees. All right, now basically the component forms are exactly what I described. I said the ball was kicked to the right and up, so horizontally the ball is moving to the right, but it's also moving up at the same time. See, we're looking for 2 vector components that form a right triangle. Okay, these are what we call the rectangular components. Well, I want to go ahead and find the speed that the ball is moving both horizontally and vertically. So 44 is the speed, the magnitude of the original ball. So if I use that, it's going to help me to figure out the magnitude of both those vectors. Is everybody okay with that? And this just goes back to good old right triangle trigonometry. One of the first things we did when we got into this unit. Okay, how can I find the horizontal magnitude, the speed of the ball horizontally? What trig function is going to help me? Cosine. That's exactly right. So I'm going to go ahead and let me erase this ground right here. So let's say cosine of, hello, come on in. So cosine of 33 degrees is equal to the adjacent, so that's the magnitude of x, over the hypotenuse, the magnitude of the original vector, 44 meters per second. Okay. Oh, feet per second. I'm sorry. I was thinking about a different problem. Okay. So how am I going to solve this for the magnitude of x? Yeah. Just multiply through by 44. These are some of the earliest problems that we were looking at. So when those cancel, the magnitude of x is about, well, let's see, 44 times cosine of 33. 44 times the cosine of 33. So let's say about 36.9. I mean, that's a pretty high decimal, but I'm going to go ahead and leave it as 0.9, even though you could make an argument to have it as 37. Okay. So about horizontally, the ball is traveling about 36.9 feet per second. Okay. Now, how high is the ball rising? How fast is that? What trig function can help me find the magnitude y? Okay, sine, yeah. So sine of 33 degrees should equal, well, we have the opposite, the magnitude of y, over the hypotenuse, again, the 44 feet per second, and then we'd solve it the exact same way. Multiply through by 44. Okay, those are going to cancel. So let's see here. 44 times the sine 33. So what should I get when I push enter? There you go. That one's got an even larger decimal, so I'd say 24 is okay on this one. Hello. So vertically, the ball is going up about 24 feet per second. There we go. Those represent the magnitudes of my rectangular components. Remember, that means the two vectors that I would add, just like we were doing in the previous problems, to get the resultant, in this case, the hypotenuse. But they just form a right triangle. That's not too bad, is it? No? I'm sorry, Matt? It is bad? Okay, where did I lose you? One more time. Yet. Yes.
Not bad yet.
Oh, not bad yet. Oh, yeah, I know the lesson you're talking about. It's the one we start tomorrow. But that doesn't mean it's really difficult. That just means our level of fun increases, right?
You know exactly which one we're talking about.
Yeah, there you go. All right. So let's try this one. Heather's pushing the handle of a lawnmower with a force of 450 newtons at an angle of 56 degrees with the ground. Okay, so same thing. I got the ground here. Oh, I did that in the previous class. Okay, give me one second. There we go. I'll just pull it right back up. Here we go. No, I'm not going to worry about that. Just pull up the file. Okay, so let me get back to where I was. Oh, where is it? We're right here. Okay. So let me try this again. So this is the ground. Okay, so draw a diagram that shows the resolution of the force that Heather exerts into its rectangular components. So I'm looking for the horizontal and the vertical vectors that form a right triangle for the resultant that we have. Who wants to come on up and show me this diagram? Okay, so let's see here. Largest we got is 27. Or Noe, you want to come up? All you got to do is draw it. All right. And remember, we're in a two-dimensional setting, so it doesn't matter if you go ahead and draw it, to the right or to the left. Okay, so you're drawing it to the left. Okay. Now, there's the resultant. Where would the terminal end be? Would it be at the ground or up above? Think about you're pushing the lawnmower. Where would the resulting force be going? It'd be going at the ground. There you go. That's right. Okay, so what we're asking is, where would the arrowhead be? Would it be right here or would it be up here? That's exactly right. There you go. And then we want to go ahead and draw the right triangle. But you can go ahead and put in the 450 newtons. You can do that. Okay. So then you have the vertical. There you go. And then show me the horizontal. Where would its direction be? The way you drew it. Would it have the arrowhead on the left or the right? So because we still need to draw the base, the horizontal component. There you go. Okay, good, good, good. That's it. That's all there is to it. So there is a, excuse me. So we have the diagram that shows the resolution of the force exerted into its rectangular components. Okay. Now B, find the magnitudes of those component vectors. That's all you want to do it? Okay. Just like the last one, yes ma'am. Okay.
Okay, so
So she's going to say cosine 56 degrees. There you go. We've got the magnitude of the resultant force, so I want to find the magnitude of these component vectors. Good. Okay, so the magnitude of the horizontal, 251.6 what? Newtons. There we go. Okay, now she's going to go ahead and set up the sine. 56 degrees equals magnitude of y, the opposite over 450 once again. There we go. $373.1 newtons. Perfect. That's it. Okay. All right. So the word problems, last week's lesson with the assignment, these types of problems, this is what you can expect on your test Monday. Okay, not the lesson that we are going to begin tomorrow. Anybody having a hard time? Anybody have any questions? Okay. Well, let's go ahead and try another one of these. Now, the paragraph before the problem here where it says recall, this is just kind of reintroducing the formulas that we've been using throughout this particular lesson. There's also different versions of it, but here's the formula that we always use to find component form, given the magnitude and theta, which starts rotating from where? The positive x-axis. We've also got the direction angle. Tangent of theta is equal to b divided by a. We're going to be using these in this problem. Okay, so let's see what it says. A quarterback running forward at 5 meters per second throws a football with a velocity of 25 meters per second at an angle of 40 degrees with the horizontal. What's the resultant speed and direction of the pass? All right, so we're trying to find the resultant, but if we look at the other problems kind of as a template, we're adding two vectors in order to get that resultant, correct? So what are the two quantities given in the problem that can represent those vectors? What's happening in the problem? Can anybody tell me one of them? Okay, the 25 meters per second, what's that represent? Okay, the football. So that's got to be one of my vectors. So let's say that the football, I'll just call that vector F. Okay, so what's the other vector represented by here? What else is moving? The quarterback. Okay, so the quarterback represents the other vector. Let's call him vector Q. Okay, so it's the same idea. I want to take these two vectors, I want to add them up, and that's going to give me the resultant vector, which is, once again, going to allow me to answer the question. Everybody okay? Okay, well, let's go ahead and find these. Now, one of them, was it the quarterback or the football? I don't necessarily need to use this formula right here to get it. Because if you're thinking graphically, one of these vectors would be on an axis. Which one am I talking about? Yeah, the quarterback. Because if I'm looking graphically, he's running horizontally, right? We're going to go ahead and believe, that the ground is nice and even for this. Okay. So he's running 5 meters per second. So if we're going to go ahead and draw it to the right, what would his component form be? 5 comma 0. There we go. Now, there's nothing saying that you couldn't set up a diagram where he's running to the left, depending on your perspective. If that's the case, then it would be -5, 0. Remember, it works just like an ordered pair. Now, the football, we can't just go ahead and tell what it is. We got to use the formula. Now, Andrew told me that the football is traveling at what? 25 meters per second. So that is the magnitude times the cosine of what? Now, is this a case where I can actually use 40? Because remember, in the last word problem, we couldn't use that 28. We had to do something. So what do you think? I can. Now, remember, theta always starts rotating from the positive x-axis. And I know that 40 degrees represents that because it says with the horizontal. If it makes a comment about the horizontal, it's talking about the x-axis. So that's going to be 40 degrees, comma. What's the second part of that? 25 sine of 40 degrees. There we go. And let's go ahead and see what those come out to be. Let me get rid of these. So we have 25 feet per second, or meters per second, excuse me. This one's meters. Cosine of 40 degrees. So I'm saying about 19.15, comma. Oops, dropped my marker. And then, let's see. Now I want 25 times the sine of 40. What should I get when I push enter here? Okay. There we go. So 16.07. Okay. And there we go. So now I have the component form for both the quarterback and the football. And we've already talked about if I add them together, that gives me the resultant. So the resultant vector. 5 plus 19.15. 24.15, comma, and then 0 plus 16.07. That's easy enough. Okay, so there is my resultant vector. Okay. Now remember, I haven't done it today. Could you solve this exact same problem graphically? Okay. How many people actually prefer the graphing method? Okay. Did you check out the video I posted about those other problems?
Oh, I didn't see the video.
Okay.
It sounds useful.
Okay. There is a video where the first two problems on this paper I solved graphically, so you can take a look at that. Okay. But let's see here. How is this vector going to help me answer the question? How would I use that to find the resultant speed? There you go. Remember, here, magnitude is the speed of these vectors. So if I want to know what the resultant speed is, I'm going to find the magnitude of this vector. Oop, went a little too far. So here's my A, here's my B. So how do I find the magnitude of component form? Emma, can you tell me what formula I'd use here? Perfect. Square root A squared 24.15 squared plus B squared 16.07. So let's see how fast the ball is actually traveling because the quarterback is running with it as he throws it. So what would you expect it to be, faster or slower than the 25 meters per second? I'd expect it to be a little faster. Okay, so let's see here. The only thing is I don't yet have the 24.15, so I need to go ahead and do a quick calculation, the 5 plus that. Okay, so now we have what I need. So control divide parentheses, okay, squared plus, now I need, what was the other one? Is it the 16.07? Okay, I'm going to square that. So this is the square root of A squared plus B squared. So what's the resultant speed? How fast would the ball actually be traveling? About 29. So we would expect it to be a little faster. It's about 29 because it's 0.01, so I'll just leave it as 29. About 29 meters per second. Okay. Does that make sense? Now, there's one other thing I need. I want to also find the direction of the pass. So what are the formula do I use here? Remember, that's the tangent formula. So tangent of theta equals, now the ratio is B divided by A. What's B? 16.07 divided by 24.5. Now, even though I use the rounded version on, my paper here, I'm going to go ahead and use the exact values in the calculator. So here's B, the 16.07. I'm going to go ahead and divide it by the A. So this is what tangent of theta should equal, the 0.665381. So now in order to find theta, I'm going to take tangent inverse of that ratio. Oop, I'm glad I didn't push enter. I knew it was going to happen. So let me get back down here. Okay. So I'm getting about 33.64 degrees. Now, is that the answer I'm looking for? Remember what we talked about last week? I always wanted you to present the angle answer the same as it was presented to me. So here, the angle was presented as from the horizontal. Is that what this represents? Yes. So this is one of those cases I don't have to do any extra calculations. It is 33 point, let's just say 6. 33.6 degrees with the horizontal. There we go. Okay. Questions? Okay, now we did skip a few problems. Like for one, I did not work this one here about the charter boat. And I'm not going to worry about this last one here that's got the video camera being hung by 3 cables. Okay, because I don't have a homework assignment for this, so I thought it best. I'll go ahead and let you guys take a look at those. Remember, the notes are already filled online. If you have any questions, come on in. I will definitely kind of help you and walk you through that. But what I want to go ahead and do, I did it early this morning. Last year, before I gave this quiz, I went ahead and had an exit ticket so people could have a little more time to get some practice in, but I didn't do that this year just because of the time factor. So I've got that exit ticket right here. This has the same information on it as the quiz that some of you just took and the quiz you took on Friday. So the grade for the class was a little low, so that's why I printed this up. This is not for a grade. This is just for your benefit. Okay, this is how some of your exam could look on Monday. So you're only going to take this if you want it. So if you want it, go ahead and raise your hand. Okay, so no. Okay, Josh, did you want one? Sure. Okay. There we go. So 2 here. Hopefully I have enough copies. If not, I can run down and make some real fast. I only made 50 this morning, because I wasn't sure how many people were actually going to take some. So I only have 2 in this row. Okay, Connor doesn't want one. Philip wants one. All 3 in this row. Adrian, you don't want one? Okay. If I can be left with just 1, I'm good. Oh, that is perfect. I'm left with 2. Oh, no, just 1. So I can still make copies for the afternoon classes. Okay. Now, what we can do with the remaining time, since I haven't passed back the quiz for us to talk about that just yet, would you like to practice any of these? Finding the component form given the initial and terminal, multiplying, adding and subtracting vectors, and the last ones are even finding a unit vector. Would we like to look at any of those together? No? We feel pretty good? Okay, if you change your mind, let me know. These answers are not posted online. Remember, this is not for a grade, but if you are looking for a little additional practice because your quiz was a little lower than you would like, definitely encourage you to go ahead and take a look at this. Okay, all right. Well, thank you very much, guys. Appreciate it. Jake.